Okay, welcome everyone to this continuation of what is tropical geometry. We are already at the power of 2 again, part 16, and I would like to kind of go closer to this idea of Gröbner bases and give you a hint how Gröbner bases are related to tropical geometry without actually mentioning Gröbner bases at all. I'm going to talk about initial terms, which are crucial somewhat to define at least tropical bases or Gröbner bases. And yeah, so these initial terms, it's kind of, we'll see what it is, but it's kind of another way to get tropical varieties, because again, tropical varieties are somewhat everywhere. There are millions of ways to get tropical varieties. This will be another one. But we start by just recalling actually what a tropical variety is. It's that thing here. This is our piecewise linear function, remember, and we kind of flatten it to the, well, you just take the points where it's not piecewise, where it's not linear, yeah, the breaking points, yeah. So we have seen 3 descriptions already, and I will recall them for you. So the breaking point description is literally what I like the most, yeah. So you have this piecewise linear function, and you just record the breaking points. There was this idea of minimum achieved twice, which is literally just equivalent to, really easy to see that it's just equivalent to this description of having breaking points, right? Minimum. That's essentially what it means to be not linear at that point. And the most exciting one, probably, so kind of these are kind of, let's say, obviously the same. It's not quite obvious, but it's not a big step between them. To go to that thing here is way more exciting, and that's really not obvious. And it was this idea of these amoebas, right? So a log of a variety. So a tropical variety is a log of a variety. And I saw you today another method or how to do this. So this is my favorite way of really kind of defining a tropical variety, and this is my favorite way of thinking about tropical geometry in general, right? It's a log of algebraic geometry, if you want. Here's another method, which is also nice to have in mind. It's also some form of a temperature zero limit of algebraic geometry, yeah? Temperature zero limit. Let's see what that means. So absolute zero, right? This is kind of the thing you kind of never really obtain, but it's kind of get arbitrarily close, right? T equals 0, temperature is 0. Okay. So we define the initial term. So you have some weight vector. There's just the powers of the t. So I will throw in a parameter t and then specialize t to 0. That's kind of the idea. Kind of the absolute 0, right? The temperature 0 limit. So I throw in this extra parameter, and then I scale to by the lowest power and set t to 0. So for example, if you have p equals x squared plus y, and you have w is 2, 3, then you just put 2, 3, then you put in just t to the 2x, t cubed y here, right? 2 t squared, t cubed. So this is t to the 4x squared, of course, and then t cubed y. The lowest power I see is t cubed, so I scale by that thing, and I get whatever something, and then I can set t to 0. And I somehow kill all the terms which have too high powers. Yeah? It already looks a little bit like I'm looking for the lowest power and look for its coefficient, but it's kind of a nice temperature 0 type method to get there, right? So for every w, fixed w, I play this game of rescaling my polynomial, and then I essentially set t to 0 after dividing by the minimal type of t that I see. So this would be a temperature 0 limit of that polynomial at that w, and it's called usually the initial term at that w. Yeah. So put in a w. Essentially, it measures how often a certain power this appears, right? By just putting in a power of t, and then kind of take the lowest one by setting everything else to 0. And I like to think of this, as I said, as a temperature 0 limit, absolute 0 limit of a polynomial. So let's do this example here. The tropical line is just that thing. So 0, 0 should be here. Somehow my picture didn't come out very nicely, so 0, 0 is here. But anyway, this is a tropical polynomial for x plus y plus 1. A tropical line for x plus y plus 1. Okay, and the initial term are monomials unless we specialize to those 4 points. In that case, they are different. And it turns out that these 4 points, yeah, so then in this case, the specialization is not a monomial. these 4 points are exactly kind of the backbone of my tropical variety, right? Here is 1, 0, 1, 0. This is, of course, 0, 0, as I already said. 0, 0. And then you have whatever, something like, oh no, this is not, of course, not 1, 0. Oh my god. This is, of course, not 1, 0, but we can fix that by just saying this one is 1, 0. And the other one is 0, 1. Now, those are exactly the 4 points that kind of make my tropical variety. And here somewhere is -1, -1, right? Somewhere here. Okay, so these are exactly the kind of the 4 backbone points of the variety, right? So the initial terms, the interesting initial terms, tell you kind of the interesting points on the variety. And that's not a coincidence. That's exactly how a tropical variety is essentially an absolute zero value of a regular polynomial, right? So this is just a regular polynomial. I play my absolute zero game. I get 4 interesting points, and the 4 interesting points form my tropical variety. And that's not a coincidence, right? So essentially, the tropical variety associated to a polynomial and this set of initial points, where it's not a monomial, they're the same, right? So they're exactly the same. So it's another way of describing what tropical variety is. So essentially, then there are 3 ways. I identify 4 if you want. I identify well, let's go back to the first slide. I identify those 2 as the same, and then we have those 2, right? Breaking point type thing, lock type object, or the third one is this temperature 0 limit. Yeah, and this is usually called Kapranow's theorem, right? They're all the same. Tropical variety, tropical geometry in this sense is either a lock of algebraic geometry or a temperature 0 limit of algebraic geometry, whatever you want it to be, right? And this is like this famous work of Kapranov, which essentially started this whole story. In essence, it says, really, if you take a polynomial and you find its zeros, its variety, its hypersurface, whatever you want to call it, and then tropicalize, that is the same as first tropicalizing the polynomial and then finding its tropical zeros, right? It's kind of a commuting operation here. And this is one of these theorems that actually started the whole story to begin with. So tropical geometry is, depending on what you prefer, either a lock of classical geometry or a temperature 0 limit of classical geometry. Anyway, I hope you enjoyed this video, and I also hope to see you next time.